Thank you very much, and good afternoon, everybody. It's 4 p.m., time for that last cup of coffee before the networking happens. My name is Andy Hock. I'm the Vice President of Product at Cerebras Systems. Cerebras is an AI computer systems company. We're building a new processor and a completely new class of computer system to accelerate computation for artificial intelligence by orders of magnitude beyond what's possible with legacy infrastructure. So today has been fantastic. We've heard a lot about the challenges scaling and operationalizing AI in the government. I'm going to talk a little bit about a different dimension of that challenge, particularly the challenge associated with large-scale computing requirements for growing AI workloads. So here's a little bit of the challenge that I think many of you are familiar with. That is, we've heard many applications, right? AI has transformative potential for the way that we process data and make decisions in both government and commercial applications. In government, for example, across transportation and security, biomedical and health systems management, as well as environment, climate, energy, and defense. So broad applicability, huge potential. But one of the principal challenges is that artificial intelligence is fundamentally constrained by computing infrastructure today. State-of-the-art models that power many of the applications that we've heard of earlier in today's sessions often take days or weeks, sometimes even months of compute time to train. This inhibits research, it inhibits innovation, our ability to test new ideas. It's costly, and from a product or application standpoint, it delays our ability to deploy new capabilities into the field against a growing volume of data that we're processing. And then once you have a trained model that works and delivers accurate results, often those trained models can't keep up with the deluge of operational or mission data that's being thrown at them in time for analysts to make AI-informed decisions about how to act next. So for example, let's just consider what's happened over the past 2 years alone in the field of natural language processing in artificial intelligence. Over the past 2 years alone, model sizes have increased by 3 orders of magnitude, requiring 1,000x more compute than they did just back in 2018. On the chart on the left, you can see down at the bottom left is a state-of-the-art natural language model called BERT that was introduced by Google in 2018. It's got about 110 million parameters or variables that can learn from the data that is presented to them. Fast forward a couple of years, state-of-the-art language model introduced by OpenAI. It's called GPT-3. 175 billion parameters, so more than 1,000 times larger. That state-of-the-art natural language model took about 4 months to train on more than 1,000 GPUs. So this is a tremendous challenge that we as a community face in scaling and operationalizing AI. And really, it's just the beginning. This is an exponential increase, and so we can imagine in the near future, multi-trillion parameter models and beyond. But why is this the case? One of the fundamental challenges is that existing computing infrastructure was fundamentally built for different kinds of work and then has evolved slowly over time to accommodate neural network workloads for deep learning, training, and inference and artificial intelligence. So they're suitable, but it's not really optimal. The individual processors themselves, because they're built to be general purpose or maybe built for other work, is underutilized. So every kilowatt hour that you throw at those processors, only a fraction of that might actually go towards useful work in artificial intelligence. And in addition, as workloads get larger, what we've done is we've built clusters of these small processors and legacy compute devices to attack those large problems. The challenge there is that brute force scaling has gotten us a long way, but it's not enough. We need more compute per device, and we need less reliance on communication between them. and more memory bandwidth. So neural network computing isn't just a compute problem, it's also a problem of data in motion and memory access. So let's take a look at a recent publication in ACM SIG-Arch Computer Architecture, which looked back at some recent data from the AI benchmark called MLPerf. And what you see here in the chart on the left is that time to train large state-of-the-art models actually falls off as cluster size increases. And so here, what we see is that as we increase the cluster size, say by 10x, or by 30x, or by 60x, we actually don't arrive at results 10x or 30x or 60x faster. We maybe actually only get 5x or 10x faster. And this is scaling out to on the order of hundreds or thousands of processors. And this is because the cost of communication between devices grows, the individual device utilization goes down, and these models actually take more epochs. The learning efficiency goes down as we scale up compute. So we need a fundamentally different solution for AI computing if we want to scale and operationalize efficiently. This is where Cerebras comes in. Cerebras was founded in 2016 with a mission to transform the compute landscape by accelerating AI. We have built a new type of processor and computer system that delivers orders of magnitude more performance to achieve a solution and insights faster. And the system itself occupies a fraction of the space and power footprint that a compute equivalent traditional cluster would take. And it's programmable with existing ML frameworks that are in use by data scientists and ML practitioners today. We're over 350 employees. As I was joking to a colleague earlier today, most people, I would say that most good hardware companies are actually mostly software engineers. That's true at Cerebras as well. We've made a significant investment in software as well as machine learning research to make this new hardware platform easy to use and help unlock completely new AI applications. We're based in Silicon Valley, so I'm on my third cup of coffee today because I'm still on Pacific time. But we also have offices in San Diego and Toronto and Japan, and we have a dedicated and experienced federal team, one of whom is here today, Mark, who is also based in the DC area. And we've got a global and growing set of customers across industry and government. The heart of our solution is a chip of our own design that we call the Wafer Scale Engine. You can actually see this in the expo hall. It is the largest computer chip ever built by more than a factor of 50. On a single 8.5 by 8.5 inch piece of silicon, we have more than 850,000 fully programmable AI optimized cores. I remember one of the earlier speakers today was recalling a time when CPUs had maybe 4 or 10, or today 20 or so cores. We have 850,000, as well as 40 gigabytes of on-chip memory and a software configurable on-chip communication network. So think of this device as effectively a cluster worth of AI computing resources all on a single chip. Just for scale, you can see that our Wafer Scale Engine, shown here at the left, is far larger than the largest state-of-the-art GPU on the market. But what the size conveys in our device is actually more of the compute and memory and communication ingredients that deliver time to solution for AI workloads. So this chart breaks down our Wafer Scale Engine compared to an A100 GPU in terms of chip size, but also in terms of compute cores, on-chip memory, memory bandwidth, and communication bandwidth. The ingredients that convey high performance, high efficiency, deep learning compute. And what you can see here is that by bringing all of these resources onto a single chip, we deliver orders of magnitude gain across all of those performance metrics compared to a traditional engine. So the advantages of wafer scale for AI compute So you have more compute, and you also unlock high bandwidth, low latency memory, as well as processor-to-processor communication all over silicon, rather than having to, say, reach out over physical wires to different memory banks or different clusters in a traditional distributed computing architecture. Once again, delivering cluster scale acceleration all within a single chip. Once we arrived, though, on this massive wafer scale processor as the right computing engine for deep learning, we had to completely rethink the packaging, power, and cooling, right? We couldn't stick a 15 kilowatt dinner plate sized computer chip into a laptop or a desktop machine or even a standard 1U data center server. And so for that, we had to really take a full systems view of the right compute solution, and our system engineering team developed the server shown here, which we call the CS2. This is our flagship product. This is what we build and sell and deliver to customers today. It's the world's most powerful single AI computer, and it fits into a standard data center rack. It's actually about the size of the refrigerator that's in my hotel room. It fits into a standard data center rack, and it connects to adjacent infrastructure through standard 100 gigabit Ethernet connections. But because the Wafer Scale Engine consumes and processes so much data quickly, we actually have 1,200 gigabit Ethernet connections. So we take in a massive 1.2 terabits per second of data into this device. So then the last question you might be asking yourself is, that's a high performance machine, but how do my data scientists or my ML researchers actually use this thing? And that's where our software team comes in. We've built a software stack that meets those users where they are. And the short answer is you program the CS2 and the Wafer Scale Engine using standard ML frameworks like PyTorch and TensorFlow. Our compiler chain in our software stack is illustrated schematically here. But the short version is you program in TensorFlow and PyTorch. Our compiler grabs a representation of your training or inference AI model at compile time and then translates it automatically into an executable that runs on our machine. So this is transparent, it requires minimal code changes, and there's no need to manually extract graphs or call lower level interaction APIs or particularly any of the complexity typically associated with programming cluster scale compute resources. You're really getting access here to a cluster scale compute resource with the programming simplicity of a single node. Many of our government customers have also asked us about lower level programming for, say, custom algorithms, custom applications in deep learning, as well as high performance computing. So this year we're also releasing a lower level software development kit that will allow users who want to program custom compute kernels for new AI or HPC applications. So the value here in performance in a new hardware platform is really faster time to solution and reduced cost to insight. So train models in days rather than weeks or months, allowing your research teams to iterate more quickly, or allowing your operations and productions teams to retrain models at a higher cadence so that they better reflect the changing landscape of data that they're presented with. Or bring larger, say, government scale data sets to train models from scratch so that they can be more accurate on those downstream tasks. Once a model is in production, our system can be used to achieve very high throughput, low latency inference, to have, say, real-time decision making, even for massive data sets. And last but not least, we really built this platform, and I come from a research background, to not just accelerate the models that exist today, but to serve as a research platform for AI researchers in government and industry to develop new techniques, new neural network architectures, new ML methods that are better suited to the problems that they face. So some of our customers, both commercial and government, we have a wide variety of customers across industry verticals. But some of them here, you'll see Argonne National Laboratory, leading Department of Energy facility for basic scientific research. The team there is using our system to accelerate, amongst other models, a model that's being used to help identify cancer drug therapy options. And that model is training more than 100 times faster on our machine than it does on a GPU, radically accelerating the research team's ability to try new ideas. At AstraZeneca, the team there was able to train models that typically took them multiple weeks in a matter of days. But as I said before, we don't want to just run today's models faster. We also want to enable new innovation. Our partners at GSK are doing exactly that. They're running our machine to train existing models faster, but they're also developing new types of neural network architectures that simply aren't practical or efficient on their existing state-of-the-art CPU and GPU clusters, allowing them to explore new frontiers, and as they say, decode the language of the cell using AI. Last but not least, back to government, we've also deployed Cerebras Systems to Lawrence Livermore National Laboratory, where they've been integrated with existing supercomputer equipment. And the team there is using our machine and AI to accelerate HPC and physics-based simulations to better understand the details of nuclear fusion. So for them, as they call it, cognitive simulation, or AI augmented physics-based simulation, it's allowing them to really open up new doors of experimentation and understand the physics for critical energy generation at a more detailed level. And last but not least, we've recently announced a set of new technology innovations in both hardware and software to not just train models that are state-of-the-art today on a single Cerebras machine, but train extraordinarily large models on clusters of Cerebras devices. We call this technology weight streaming. This is an architecture to support extreme scale models with the same push-button software ease. What it does is it disaggregates the different memory requirements and compute requirements unique to AI computing. And we take the memory associated with model parameters, we store those on technology that we call memory X, and then we stream the model in to the compute substrate, the CS2. This disaggregation of memory and compute uniquely supports up to 120 trillion parameter models on a single CS2 device. So recall that GPT-3 today is on the order of hundreds of billions of parameters. We as a community are sort of pushing at the envelope of trillion parameter models. This technology allows on our infrastructure to support orders of magnitude larger models than that. And to go faster, we've also developed software and networking technology to tie these machines together efficiently and cluster Cerebras systems with near linear performance scaling up to 192 CS2 systems, going well beyond exascale computing for AI. And last but not least, the wafer processor that's the heart of these systems, as I mentioned in the beginning, is really designed from the ground up, not to be a general purpose processor or do different kinds of work, but really is intended to accelerate sparse linear algebra for computationally intensive AI and HPC workloads, but also allows researchers to more efficiently experiment with sparse processing, sparse data sets, sparse models, so that we can build not just larger models, but also models that are more parameter efficient and more efficient with the data that they're presented with. So this technology allows us, imagine, to train a model on the scale of a GPT-3, not in months on thousands of processors, but maybe in a day on a modest cluster of Cerebras systems, or train a trillion parameter model over a long weekend. Really excited to share this with you today. From scaling compute for research and production, what we're seeing is a growing interest in high-performance compute and building of heterogeneous compute infrastructure that leverages best-of-breed architectures for different parts of the end-to-end data science and ML workflow. Our machine, you can really think of as a high-performance accelerator for this. The CS2 is the most powerful system available today. At its heart is that 850,000 core wafer scale engine. And our new work with weight streaming is going to allow us to unlock far larger models with more reasonable training times so that we can iterate as a community more quickly. So I'll conclude by saying thank you. Particular thanks to the folks that are here in person today. I know it's interesting to be back at a conference in real life. Thanks also to the virtual attendees and the conference organizers. If you're interested, please visit us in the expo hall. There's good coffee in there, and we have a wafer. We would be happy to chat more. If you're interested in a system or in a pilot, as we've heard, lots of pilot interests, we're actively hosting those. Feel free to reach out to me personally or find Mark in the expo hall, or you can also find us online. Going into the future, we've done quite a bit of work to enable our customers. We can deploy directly into data centers. We can host systems. You can rent time on them. And we've recently announced a cloud partnership with a company called Cerebras Scale. So if your organization is cloud native, we can work through that as well to provide broader access to extraordinarily high performance AI computing. And I hope that we can work together to discover the benefits of that for government applications. Thank you.
We might have time for one question.